Hi guys, can someone tell me if you're able to hear me? I'm not able to see the chat. Again, it's a new problem. Okay, guys, we'll get started. I'm not able to see the chat window. It's YouTube is giving some error, but I hope you guys can hear me. Okay. Cool. So let's get started. We'll solve the first problem. Okay, I can see the chat on my phone. Okay. So we'll start with a question called same tree. Okay. So in the previous class, I think we have discussed our in the live classes we have discussed the basics of trees, and we talked about tree traversal, right? Let me start uh, our. Let me get our notebook for live sessions. Okay. So far in our discussions, we have talked about linear data structures like okay, we have talked about array, and we have talked about linked list. We have talked about stack, and we have talked about queue. Okay, so today we are going to start our discussion with non-linear data structures. So our first data structure that we are going to talk about is trees. Okay, and I've given you some introduction about trees, so I'm not going to go into much of the theory part of trees, and especially tree traversal. So within tree traversal, the most important thing that you need to know in trees is of course the basic terminology around trees, like what is a root node, what is the parent node, child node, sibling nodes, what is the depth of a tree, what is the height of a tree, but most importantly tree traversal. Okay, and tree traversal, we saw that there are two types. One is the depth first and the other is breadth first. Okay, breadth first is also called as level order. Okay, so these are the two concepts that we have seen inside DFS. We have talked about pre-order, post-order, okay, and in order. And we are not going to do these today. These are the basic things that you need to know in order to get started with trees, but today we are going to solve some problems. So let us quickly jump into the problem, and this is the first problem that we want to solve, where let us first read the question. Okay, the question is about, question says same tree. Okay, so let us read the question. Question says that given the root of two binary trees. Okay, we've been given root of two binary trees P and Q. Write a function to check if they are the same tree or not. Basically, two trees will be given to us, and we need to return a boolean whether the two trees are same or not. Now, just by reading this line, you might start thinking about what might make us decide if the two trees are same or not. Of course, all the nodes should be same. All the children, left node, right node, everything should be same. And we have discussed extensively about the recursive nature of trees, right? So you might want to apply that logic somehow as to how we could use recursion here. Two binary trees are considered to be same if they are structurally identical and the nodes have the same values. Of course, we know that. Okay, so let us see some examples here. Okay, so the example here is this node. So this is P and this is Q. So P is the reference to the root node and Q is the reference to this root node, the second root node. And this node is same, fine. So it is good. If these two nodes were different, if suppose P was not equal to Q, then here itself we could have returned false. So here P and Q are equal. So what are we checking? We need to check the left child of P and the left child of Q. Okay, so this is also equal, that is great. And then we need to check the right child of P and the right child of Q, which is also equal, right? So it could have been possible that the right left child of P and left child of Q were not equal. In that case also we would have returned false, or similarly for the right child also. Now here we just have two nodes as right child and left child, but it is possible that we have a tree on the left and right side. Okay, so let me give you an example of that. Let us take this question and in our notebook and try to explore it. Let us see one more example is there. See, this example is there. Okay, so these two are not identical. This is P and this is Q. P and Q are equal, fine, but the left child of P is 2 and there is no left child for Q. We have null, right? So this 2 and null are not equal, so that's why this is coming out to be false. I hope this example is clear. And here again you can see that these two trees are actually inverse of each other. So later on we'll also look at a problem where we have to decide if two trees are mirror images of each other. So these two trees are mirror images. So this is P and this is Q. The left child of P is 2, but here it is 1. So this is also false. Okay, so let us now try to write a general logic on how we can check if two trees are same or not. Okay, you guys following? Cool. So let us come here and let us take a new file, new page, and let us say Leetcode 100, and the question is same trees. So just for example's sake, I'm going to take two trees which will have further subtrees. So let me take P as maybe 1, and then here I have 2, and here I have 3, and here I have 4 and 5, and here I have 6, and here I have 7. Okay, and I'll take another tree here which is again 1, 2, 3, 4, 5, 6, and 7. Okay, so if I'm given a task to check if these two are equal or not, okay, and I'm labeling this as P and labeling this as Q, so definitely we need to check that P and Q should be equal. P and Q should be equal, right? If P and Q is not equal, then here itself will return false. We don't have to check anything, right? It is also possible that I have P but there is no Q. Okay, or I don't have P but I have Q. These two cases also we can immediately return false. Basically we need to make sure that P and Q are existing and P and Q's value are same. When I say P is equal to Q, I basically mean P dot value is equal to Q dot value. I hope you are understanding that. Okay, so first step is to check the root node. Both the root nodes should be present, and both the root nodes, if both the root nodes are not there, suppose P and Q both are null, then what will be the case? I'm just noting down the first edge cases. Okay, let me bring it here. Okay, and one case here can be that I don't have P, I don't have P, and I don't have Q. So if P and Q both are not there, then I can return true. Okay, because both trees are identical if they don't exist, right? If either of p and q are not present, then also we need to return false. If p and q are present but their values are not equal, then also we need to return false. And if p and q are equal, then we need to further go and check a few things, right? What do we need to check? We need to check that their left and right children are same, right? So if we are writing a function called same tree, okay, to check for p and q, and this is the idea that we have discussed a lot in recursion, the same function can also be used to check if the left subtree of p and the left subtree of q are equal or not. So we also need to check that if same tree p dot left and q dot left and same tree p dot right and q dot right. So recursively the function will call, first it will check for p and it will check these conditions, right? Once these conditions are met, if p and q are both equal, then we need to check if the left subtree of p and left subtree are equal. And how will we check that? We'll use the same function which we are using to check the main node, right? And then we'll check this condition. So if we use recursion, then basically we need to check p and q are equal and p ka left subtree is equal to q ka left subtree, p ka right subtree is equal to q ka right subtree. Are you getting it, guys? So what's going to be our logic? If we try to write some code here, I'm calling it pseudocode, but actually we are just going to write code itself. Okay. So what are we going to check first? We are going to check if not p, if not p and not q, then we will return true. Okay. If not p and q or p and not q, I'm using this and operator, but actually you will use and p and not q, then we will return false. Okay. If p dot val is not equal to q dot val, then we will return false. Okay. I hope all of you are following till here. And all of this we are doing inside a function which is called sub same tree. Okay. This is the job of a function which is same tree. So here I'm having a function called same tree which takes p and q. Okay. If this much is done, then what do we need to check? After that, we need to check. Uh, we can say we can create one variable called same tree. So you see, I'm calling the same function inside this. So I'm going to say same tree p dot left and q dot left. Okay, so p will become p dot left, q will become q dot left, and same tree p dot right and q dot right. I'm going to return this. So let me put this as a variable. Let me say same is equal to, and I'm going to return same. Okay, so this is the entire function. This is the recursive solution. Guys, able to follow? Let us try to write the code. Okay, so you see we have been given one function here is same tree. I'm going to use that function again. So I'm going to say if not p and not q, I'm going to return true. Okay, I'm going to say if not p and q, sorry, p and q, or let me put this as a bracket. I'm going to say if p and not q, then I'm going to return false. They are not same. I'm going to say if p dot val is not equal to q dot val, then I'm going to return false. Okay. So now if these conditions are not run, that means both p and q are there and both of them are equal. So if p and q are present and both of them are equal, that means I need to check the left subtree and right subtree. So I can just return is same tree. Okay. P dot left and q dot left. So the left subtree should be same and the right subtree also should be same. So I'll say is same tree p dot right and q dot right. Okay. I can say this is my same and I will just return same, or you can directly return here. No need to assign a new variable. Okay. So let me say here if p and q are equal, then check for left and right subtrees are both same, are both equal. Okay, so let us run this. Is same tree is not defined, self dot. Okay, you can see this is running, and then okay, so this is running, this is fine. Let me take this question and put it in your sheet. Okay, let us move and let us do the next question. We can also actually kind of add this question to our sheet. Actually, in our sheet, we don't have tree questions as of now. BFS, DFS में ही tree का questions also I have mixed actually. I'll create a new section called trees here and I will add the question. Okay, so you can see this sheet later on. I will add the questions. Okay, so let me mark this as done and let us move to the next question. Okay, let us do one question which is mm, max path sum, path sum. Let us do this one. Okay, let us read the question and try to see. I hope all of you are following, guys. Let me see the chat. Tyler, Sumit, Anupriya, are you guys following? Let us read this question. And so this question is given the root of a binary tree and an integer target sum. Okay, so we will be given a binary tree and an integer target sum and return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. Okay. Let us try to understand the question first. So this is a tree that has been given to us, and we have a target sum of 22. Okay, target sum of 22. So basically the question says that is there any path from root to leaf? Okay, so what are the possible paths from root to leaf, guys? This is one path, this is another path, this is one path, and this is another path, right? So there are four possible paths from root to leaf. So it is saying that is there any path which contains the sum 22? So if we take 5 plus 4 9 plus 11 20 plus 7 27, so this path is not correct. Okay, 5 plus 4 9 20 plus 2 22. So there is existing one path which has been highlighted in blue here. Okay, let me also highlight it in, say, purple color. This path, okay, this path is from root to leaf, which adds up to the sum 22. Okay, if we take this path 8 plus 5 12 plus 13 25, this does not work. 8 plus 5 12. Okay, this path 8 5 plus 4 9 20 27, 9 20 22, 8 5 13 13 13 26. No, this does not work. 8 5 13 plus 4 17 plus 1 18. So this path also does not work. So there is one path. Okay, so in this case we found a path, and we found that sum 22, we were able to get it. Okay, let us see another question. I hope the question is clear, guys. We are looking at another example here, and here we have 1 2 and 3, and the target sum is 5, right? So if we take, there are only two possible paths, this path and this path. So here the sum is 3 and here the sum is 4. So we are not getting the target sum, so here the answer is false. Okay, let us see one more example, if we have another example. Okay, if we don't have a tree, if we don't have a tree, then there is no sum possible, right? Since tree is empty, there is no root to leaf path. So we know that there is one edge case where it is possible that our root is empty or tree is empty, there are no nodes. In that case, we need to return false. Okay, so we can look at the constraints. So you can see here in the constraints that the number of trees in the range 0 to 5000. So 0 nodes are possible. So if 0 nodes are possible, what we need to do, we already know here. Guys, all of you are following? So can you think of again a recursive approach that will help us here? Usually in these type of questions, we should be able to come up with a recursive solution. So 112 path sum. Let us come here and see. Leetcode 112, which is path sum. If you are able to break down the problem into sub problems, then you will be able to come up with a recursive solution. Let me copy paste this example itself. Okay, so this is the example that has been given, and here the target for us is 22. Okay, so you see, if we start at the root node, we have to start at the root node, right? There is no doubt about that. If we start at the root node, okay, and our target is 22, and here we have 5, right? So 22 minus 5, okay, 22 minus 5 should be the sum of either the subtree of this and subtree of this, right? We are looking for a sum of 22 in this entire tree, right? What I'm trying to show you is how to break down the problem to sub problems. We are looking for a target of 22 for this entire tree. If we take this node out, if we take this node out, then if this tree, if the left subtree, if the left subtree, if this subtree has a sum of 17, okay, or if this tree has the sum 17, okay, then we can say the entire tree has the sum 22. Can we say that? So if we need to look at this tree for 17, right, then what we need to do? We need to remove this 14 from here. Okay, so if this becomes 14, then 17 minus 4, okay, 17 minus 4, I need to look for 13 in either this subtree or in the right subtree. In this case, 4 does not have a right subtree, right? So I need to look for 13. So if I look for 13 in this subtree, I'm looking for 13 in this subtree. Okay, I'm looking for 13 in this subtree. So 13, if I take this node, then I will do 13 minus 11, which means I'm looking for a 2 sum in this subtree or 2 sum in this subtree. Are you getting the point? Whichever node we go, we subtract that value, and the remainder amount we are looking for either in the right subtree or left subtree, right? So here we are getting a 2, which means that this becomes a valid path. This becomes a valid path. Okay, we did not check the right side, so we can check the right side also. So here we were looking for 22. If we take out 5, then we are looking for 17, right? So we want 17 in this subtree. So if we want 17 in this subtree, then we have to do 17 minus 8. Okay, so we are looking for 9 here or here. So here we cannot get 9 because we already have 13. Here also we are not getting a 9 because already this is 4, so we have to look for 5. We don't have a 5, we have a 1. So right side we don't get 17, left side we are getting a 17. Guys, did you follow? So what we have to do? Whatever is the path sum, okay, whatever is the path sum, we need to find, first we need to find the remaining amount, remainder amount, which is the target sum minus root dot val. This is the target sum. Okay, and this remainder should be fulfilled by either the right subtree or left subtree. Keep in mind that we are writing one function here which is path sum. Okay, and in path sum we have the root and we have the target. Let me make it target here. And if it is the recursion, we need to think of the base case. So if you remember in the previous question, these were our base cases. These were our base cases. So here, what is the base case? We'll think of base case, but I want you to think first about how we are breaking down the problem into sub problems. Okay, or self similar problem. What we are saying is that if we want 22, I'm explaining it again. Someone is asking, Bhavish. Okay, so I'm explaining it one more time. The basic idea. Okay, code will have some edge case handling that we will see. What I'm saying is, if this bigger tree, we for this bigger tree we need a sum of 22. Okay, can I say that for this subtree I want a sum of 17 because 5 is here? So if this tree gives me 17, then this whole tree can give me 22. When I say this subtree gives me 17, I mean in this subtree is there a path sum of 17? What is the definition of path sum? From root to node. Okay, so I'm saying, can this path or this path give me 17? If it can give me 17, then this tree can give me 17, the left subtree. If left subtree gives me 17, then added with node, root node, this entire tree can give me 22. So if I'm saying this subtree, now my problem becomes that 4, can 4, 11, 7 and 2, can this tree give me 17? Okay, so if I break down this problem, then I'm asking a question, can 11, 7 and 2 give me sum of 13? Okay, this I'm further breaking down into a problem, can 11 and 7, okay, sorry, can the left subtree What did I say wrong? Let me break this. Let me break this down. 5, 4, 11. 5, 4, 11, 7 and 2. And here we have 8, 13, 14. 8, 13, 4 and 1. Okay. So for this entire tree, I need a sum of 22. Okay. This I'm breaking down into a sub problem where I'm saying, can this subtree, which is 4, 11, 7 and 2, can this subtree give me a sum of 17? Okay. And or 8, 13, 4 and 1, can this subtree give me a sum of 17? Either of them. Okay. Now this becomes the same problem as this problem. Do you understand that? This is the this is the whole point, that whatever function we are using to solve this problem, same function will be used to solve this problem, because these two problems are similar. In both the cases, we have a tree and we have a target, right? And this problem can further be normalized by saying that I want either 11 and 7 to give me a sum of 13, or I want 11 and 2 to give me a sum of 13. Okay, so this is valid, this is giving me true, which means that this path giving me the answer. Did you understand? Okay, so what I'm saying here is, we will have a path sum and we'll find a remainder is target minus root dot val. Of course, if we don't have a root, did you understand, Bhavish? Okay, and this is a common pattern. You'll see that in this problem also we did the same thing. Okay, we checked for p and q, we checked if p and q are same, and then whatever function is being used to evaluate the whole tree, same function is being used to evaluate the subtree also. That is only recursion. Okay, self similar pattern, we are breaking it down. Okay, so what we'll do, we'll say if not root, if not root, if root is not there, okay, then we'll return false. This we already know, this was our base case. If you remember, here we did that if we don't have any root, then we are going to return false. Okay, this is one case. After that, if we don't have children, if we don't have children, okay, then what will happen? Suppose I'm giving you just one tree like this 5, and I'm asking you if target can be 6. You will say false or true, you can decide immediately. So we'll say if no children, if no children, these are the edge cases. And I told you, in recursion, edge cases are those cases for which we know the answer. So in this question, under what situation will you know the answer? You will know the answer if there is no node, or you will know the answer if there is a single node without any children. So I'll say if not root dot left and root dot right, like this. Okay, we will return, we'll return what? We'll return root dot value is equal to target. Then we don't have to check anything. If the root dot value is equal to target, then true, otherwise it is false. Otherwise, we need to calculate the remainder. Okay, and we need to check if the left subtree has the remainder or the right subtree contains the remainder. So we'll say same function we'll call again. We'll say path sum, path sum root dot left. Actually, we should not have root here. Uh, is root okay? रूट डॉट लेफ्ट, हाँ रूट डॉट लेफ्ट इज फाइन. आई वाज थिंकिंग शुड वी मेक इट नोट, नहीं ठीक है. रूट डॉट लेफ्ट शुड हैव रिमाइंडर और पाथ सम. रूट डॉट राइट should have the remainder. If either left subtree should return or right subtree should return, and we will return this value. इसको थोड़ा मैं नीचे कर देता हूँ. सॉरी, थोड़ा सूडो कोड अजगज हो गया, बट यहाँ पे ये रिटर्न हो जाएगा. ठीक है, दिस इज द फंक्शन. डिड यू फॉलो गाइस? हाई लेवल लॉजिक डिड यू अंडरस्टैंड? नोड हटा के जो रिमाइंडर बचा वो रिमाइंडर लेफ्ट सब ट्री से या राइट सब ट्री से मिलना चाहिए. तो लेफ्ट सब ट्री में फिर से हमारे पास एक लेफ्ट सब ट्री है विच इज ऑल्सो अ ट्री. एक ट्री है और एक टारगेट है. फिर उसमें से उस सब ट्री का नोड हटा के उस ट्री को ब्रेक डाउन कर देंगे. उस ट्री का लेफ्ट और राइट हमें मिलना चाहिए. ठीक है, ये कब तक चलता रहेगा? टिल व्हेन विल दिस गेम go on? Till we reach a null node. Okay, when we reach a null node, that time the function will be able to return a value. Otherwise the function will keep calling itself. Okay, chalo, let us try to write our logic. Okay, so what did we decide? We decided that the first case is if there is no root. Okay, so we'll say if not root, then we will return false. कोई कह रहा है कि रूट नल होगा तो इट विल ब्रेक. नहीं, रूट नल होगा तो ब्रेक नहीं होगा. दैट कंडीशन वी आर हैंडलिंग एंड दैट कंडीशन वी हैव टू हैंडल. What do we know about this question? When we read this question, what can we conclude? Or under what situation do we know the answer already? We know the answer if we don't have any node, if node is empty, or if there is only one node, right? If there is only one node in the tree and there is a target called 6, then you can check if there is no children, then this 5 should be equal to 6, right? So if children are not there, then root node ka value should be equal to target ka value. We know this. Okay, in order to solve this situation we don't have to do anything. If the node is empty, there is nothing, then whatever is the target, suppose target is 10, we have to return false. Okay, this is one case. Another case is that we have to return root dot value is equal to target. These two are our base cases. Okay, ultimately we are going to reach one of these situations. Until then we will keep breaking down the problem into further problems. Okay, so we'll say if not root, we will return false. Okay, second case is if there are no children. Okay, then we'll say if not root dot right and not root dot left. Okay, then what we'll return? We'll return root dot value या data value is equal to target या target sum है, target sum. Okay, otherwise check if either left or right subtree is having a path sum of remainder. Okay, so what is the remainder? Remainder is equal to target sum minus root dot val. Okay, and we need to return क्या नाम था फंक्शन का? has path sum root dot left root and then target sum. So target sum becomes remainder. Okay, or has path sum root dot right remainder. ठीक है, चलेगा? क्या हो गया? यहाँ पे सेल्फ आएगा ना? This is working, guys. By the way, what is the time complexity of this? What is the time complexity? Every node will be compared, right? So this is linear O of n. Okay, and what is the space complexity? Are we using any extra space or anything? No. Okay, so you can say O of 1. Space complexity, someone can say O of n because we are using recursion, so recursion stack will be there. Okay, but we can say O of 1. Space complexity can be O of h, which is height. Hmm. O of 1 ही होगा, वो रिकर्जन वाले को नहीं कंसीडर करते. O of 1 ही बोलो आप, ठीक है? तो सबमिट करते हैं. ठीक है, ये भी हो गया. पाथ सम, इसको मैं डाल देता हूँ शीट में. Guys, are you following the approach? Let us do one more question. Uh, Similar question. Uh, Same pattern I'm doing today, which is recursion, very classic recursion. We'll do invert binary tree. Very interesting question. Okay, later sometime I'll also show you the iterative approach for this. Okay, we are doing recursive approach, but we can also do iterative approach. And in iterative approach, we need to decide whether we are doing a depth first or breadth first. If we are doing depth first, then we'll use a stack, and if we are doing breadth first, then we will do a use a queue. Breadth first, I have not shown you the basic level search also that we will do on our weekend class. But let us solve this question. It is interesting. Okay, then we will stop for today. 9:45. We have 15 minutes. We can do. Question says invert a binary tree. Okay, invert means we need to convert it into its mirror image. Okay, given the root of a binary tree, invert the tree and return its root. So as it is, we have to return it. Means we don't have to create a new tree. So you can see this example. We have 4, and then you see 2 and 7. So imagine that you have put one mirror here. Okay, so this 7 comes here and this 2 comes here. Okay, and this 1 and 3 are also reversed. You can see this 9 is here, 6 is here, 3 is here, and 1 is here. So I hope you can imagine what mirror image is. Okay, so very simply, if this is 1, 2, and 3, so if I put a mirror image here, then this becomes 1, 3, and 2. Okay. Question is clear, guys. Let us see one more example. Similar example. Okay. So if you want to break down this problem again, and if I give you a very simple case, which is if there is only one node, 4 and 4, then already it is a mirror image. We don't have to do anything. right? It is already a mirror image. We don't have to do anything. If we don't have a node, which is an empty node, sorry, uh, made a mistake, sorry. I wanted to say that if you just have one tree is just having one node, then this itself is the mirror image. Okay, this itself is the mirror image. And if there is no node, suppose it is an empty node, okay, then there is no mirror image here. Okay, so we can return none. We can ask for, we can check what will happen. See, if empty situation, if it is empty, we have been told that if it is empty, then we need to return null. We don't have to return anything. Okay, so let us go back to our sheet and then try to explore it. This is question 226 in word mandatory. Okay, so suppose if I ask you for what will be the base cases or for what situation we know the answer. If it's an empty node, okay, if not root, okay, then we need to return none. It has been given, okay, empty. When it is given empty list, that means it is none. Okay, otherwise what you need to do, suppose if you are given like this 1, 2 and 3, then what we need to do to make it as reverse? Okay, the left child and the right child, they need to be interchanged, right? So this has to become 1, 3 and 2, correct? So the left child and right child need to get swapped. Bhavesh, what you are saying is absolutely correct. Okay, so it basically means that root dot left and root dot right should actually become root dot right and root dot left. Okay, is this sufficient? Okay, we will come here. Because I've drawn a very simple example, but you'll see what will happen after that. So we'll say this is our function in word tree. We are given one root. So if root is not there, then we'll return none. Otherwise, if children are there, then we will swap the children. Fine. But what if we were having like this 2, 3, and then 4, 5, 6, and 7? Okay. What will happen here if we swap it? What will happen when we swap it? We will get this, right? We will get 3, 6, and 7. Okay. And we will get 2, 4, and 5. Is this correct? No. This should actually become 7 and 6, and this should become 5 and 4. So 765654 7654. So actually the children, they again need to be swapped. So I swapped the left and right child of this. Then I also need to swap the left and right child of this, and I need to swap the left and right child of this. Which basically means that if I am doing an invert on this node, then I need to swap the children, and then after that, after swapping, I need to call invert on. After swapping, I need to call invert on this and call invert on this. Are you getting it? Priyanka is saying if root dot left and not root dot right. रूट डॉट लेफ्ट एंड नॉट रूट डॉट राइट भी अगर रहा, ठीक है, मतलब चिल्ड्रन नहीं रहा, ठीक है, सपोज ऐसा नोड है, चिल्ड्रन नहीं है, तो भी ये वाला सिचुएशन उसको हैंडल कर लेगा ना, क्योंकि अगर ये नल है, ठीक है, तो नल अगर स्वैप हो जाएगा, ठीक है, तो इसको मैंने जब स्वैप कर दिया, तो फिर से यहाँ पे स्वैप करने के बाद फिर से नल है और नल है, ठीक है, फिर जब उसके बाद इस पे इन्वर्ट कॉल करेंगे और इस पे इन्वर्ट कॉल करेंगे, तो ये वाला एज केस उसको हैंडल कर लेगा, तो वो हैंडल्ड है ऑलरेडी. Okay, did you get why we have to call invert again? So we have to swap and then invert the children again. So what we have to do here, we have to call invert tree on root dot left, and then we need to call invert tree on root dot right. Did you get it, guys? After this is done, then we need to just return what we need to return. Nothing we need to return, because already, does the question say we have to return? Question says return the root. Okay. So why should we return the root? Root will be there. So what is the point of returning the root? Fine. Okay. Can you see? Can you understand, guys? This is also a concept of breadth first search. Breadth first search I have not discussed right now, but we can also solve it using queues. That I will discuss later. Okay. So you can add one in the queue, then children of one in the queue 2 and 3. Then you can DQ1 and invert it. Then you can DQ2 and invert it, DQ3 and invert it. When you DQ2, add the children of 2, 4 and 5. Like that, we can also do a breadth first search. So we'll discuss breadth first search in our weekend class on Saturday. But for now, because we are talking about recursion and I want you to internalize breaking down a problem into recursion, so that you are able to identify some recursive patterns. Right? If you see recursive pattern, then code becomes simpler. So this is the recursive solution. What will be the time complexity? O of n. Let us write the solution. Okay. So what is the solution? If not root, then we'll return none. Otherwise, we will swap the left and right children. Root dot left, root dot right is equal root dot left, root dot right is equal to root dot right and root dot left. ठीक है. उसके बाद invert the children. Child trees. We'll say invert tree root dot left and invert tree root dot right. ठीक है, फिर रिटर्न कर देंगे रूट को. Actually, the space complexity, and technically it is not O of 1, it should be O of h, because we are using a recursion stack. और recursion stack में कितने बार ये function call होगा? How many times are we going to call the function? We are going to call this function the same number of times as there are levels. If there are 3 levels, we'll call it 3 times, right? सो स्पेस कॉम्प्लेक्सिटी ओ ऑफ एच होना चाहिए. पिछले क्वेश्चन में भी वो ओ ऑफ एच होना चाहिए. ओ ऑफ वन मैंने बोल दिया. मैं एक बार चेक करूंगा कि क्या उसका एक्सेप्टेड आंसर है, बट इट शुड बी ओ ऑफ एच. क्या हो गया यहाँ पे? अरे चल गया, ठीक है. इसको भी मैं शीट में डाल देता हूँ. Guys, did you understand all the three questions? We are out of time now. So एक और क्वेश्चन सॉल्व किया ना हमने, पाथ सम पर. ये दोनों को भी डन मार्क कर देते हैं. विल एवरी प्रॉब्लम वी यूज? नहीं, हर क्वेश्चन में रिकर्जन नहीं होगा, बट रिकर्जन इज अ कॉमन पैटर्न. एक्चुअली दीज आर ऑल ट्रैवर्सल प्रॉब्लम्स. द ट्रैवर्सल प्रॉब्लम जब हमने पढ़ा था, ट्रैवर्सल, पोस्ट ऑर्डर, प्री ऑर्डर, तो उसमें आई गिव यू रिकर्सिव सोल्यूशन एंड इटरेटिव सोल्यूशन. सो दीज आर एक्चुअली ट्रैवर्सल प्रॉब्लम्स somehow. Okay. But recursion becomes easier to write. You remember when we were doing the iterative approach and we spent so much time on the stack approach, and sometimes that stack approach also seems little tricky, that it may or may not click, at least from my personal experience. But recursion, if you are able to spot it, if you are able to spot recursion, then it is easier to solve it. You just have to figure out what is the base case and then write the recursion. But it's not that always you will use recursion. But very often you will use recursion. Okay, guys, we have solved three problems. We'll stop here today, and I'll see you again on Thursday. Again, we will take up trees and we'll try to solve four more problems. Okay, we'll also try to do some breadth first search on next session. How did you like the session, guys? That's all for today, and please share the live link with your friends. It's open for all; anyone can join, and you can also check out my channel. So this is my channel. You can check out the basic Python videos, and there are some DSA videos also. I've not uploaded in a while. There are only 3 videos, but I'm working on array and graph videos also. So I'll upload it very soon. Okay. That's all, guys. Thank you, and I'll see you. Good night.